Good evening, everyone. Welcome back to NPTEL live session, and this is the last session for this particular course. And today we will be taking up all the left out topics. So, for example, some oxidation related stuff and hydrogenation examples. And we'll be compiling all the things, and at the end, we will be having a problem session. So, before starting that session, we will wait for a few more minutes for others to join. And if you have any other question or doubt, please let me know in the comment section. Thanks for joining. We'll be shortly starting the session. Thank you. We can start the session now. So our topic of today's session, we are going to start with the hydrogenation of alkenes. So for the better network, I'll keep my video off. If there is any doubt, please let me know. So hydrogenation of alkenes, basically, it's a complementary reaction to the oxidation of alkenes because in the end, we have seen the Monsanto acetic acid preparation where if we talk about like how we have converted what we have done in our earlier reactions. So in the previous session, we have seen the oxidation of the alkene, making it epoxidized. Various example, asymmetric oxidation, everything that has been taken into consideration. Now, this is basically the reduction of alkenes, or you can call it as a hydrogenation. So this is a complementary reaction to the oxidation of alkenes. And here, so H2 is the source of hydride, and for this also this needs to be activated. And the activation of dihydrogen in homogeneous solution. So everything is occurring in a homogeneous medium. It can be achieved by, so there are three ways. First, we can have a homolytic cleavage. Homolytic cleavage would be meaning homo means same and cleavage is breaking. So the both the hydrogens will take one electron each because one bond is having two electrons. This would be called as homolytic cleavage. So in this scenario, if we are taking a cobalt cyanide complex and treating it with hydrogen, now hydrogen activation is going to happen. And in homolytic cleavage, both because there are two molecules, each molecule will take one proton, forming two CO, CN5, H3 minus. So this has been cleaved as H dot and H dot, and both of them has taken one. If we talk about now, the second that we can talk about is heterolytic cleavage of hydrogen. And heterolytic cleavage itself tells that how it is going to break. That means you have H and H. One will take the electrons, making the other one as proton, and the one which has taken the electron that becomes as a hydride. So this cleaves into a proton and a hydride. This is called as heterolytic cleavage. Now here we have an example where we are taking the platinum SnCl3 whole 5 3 minus. This is a complex, and here we are treating with H2. So what happens here? Platinum will take your hydride, forming SnCl3 whole 4 3 minus. One H plus will go out because a proton will be released, and one SnCl3 will be going out. So this is how heterolytic cleavage of hydrogen would occur. And the third important mechanism or way of leaving your hydrogen or activating your hydrogen is oxidative addition, which is generally followed in case of uh, coupling reactions or organometallic reactions. So here we have, so in oxidative addition, what is the mechanism basically? If you have M in N plus oxidation state, having ligands around, when you are giving H and H, it would get bind with your system, and your oxidation state of metal is now N plus 2 because one electron has been given to each proton, each hydrogen. So this is called oxidative addition. So here we have an example. We are taking a Wilkinson catalyst, which we will be talking about later, PBH3 rhodium chloride in presence of hydrogen. What it would form. So it would have a PBH3, two PBH3 molecules will go out, and rhodium will be having two hydrogens. Now here we are writing H bracket 2, meaning both the hydrogens have been cleaved and Cl. So basically it would be having rhodium H HCl and PPH3. So this kind of structure where both the hydrogens are onto the same metal system and acting as a oxidative addition, acting as a result of oxidative addition. So these are the three different methods how we can activate the hydrogen which is required for hydrogenation of the alkene. Now let's start with the process which is your hydrogenation of alkenes. When we are talking about hydrogenation of alkenes, generally we are talking about the catalyst also. So here we are talking about Wilkinson catalyst. Name is important. Sometimes just the name has been given and there you need to define what is what. So Wilkinson catalyst. Now there are certain features that we need to keep in mind. Firstly, the first practical application of the homogeneous hydrogenation catalysis. Hydrogenation catalyst is this Wilkinson catalyst, which is nothing but triphosphine rhodium chloride. This is very important complex where rhodium is in plus one oxidation state because your phosphine is a neutral ligand. This actually involves the oxidative addition process of dihydrogen The another features are hydrogenation of alkenes and alkynes, they occur at or they happen at 25 degrees Celsius, which is the room temperature, and at standard pressure. So it does not require any harsh reaction parameters. Also, if we compare a terminal double bond be it of your alkene or alkyne, that would be faster compared to the internal double bond for hydrogenation. So if you have a choice, which one is going to give you a faster product of hydrogenation? The terminal one would be giving at a faster rate compared to the internal one. It does have a functional group tolerance for NO2 and aldehyde group. That means if you have NO2, nitro or aldehyde in your substrate, alkyne substrate, that is not going to hydrogenate into NH2 or methanol or something. It is not going to happen in that way. So it is having a functional group tolerance. And this also we know that the dihydrogen activation or addition on the Wilkinson catalyst that happens on the N cis fashion. So whenever they get added, they will add in a cis fashion, not in a trans fashion. So this we need to keep in. So these are the features of a Wilkinson catalyst performing the hydrogenation. Let's quickly look into the mechanism of Wilkinson catalyst performing hydrogenation of alkenes. So as I mentioned, we have P3RHCl, where we are just saying that P is your PPH3. It is easy to write over here. So if it loses one P, ultimately you will be having the structure like 2 and Cl. And if you add again back from here to this side, then it would be reclaiming your catalyst. So firstly, for having the oxidative addition, it needs to lose one phosphine group. Now, first step would happen, as I said, we will be introducing a hydrogenation, hydrogen dihydrogen, and this is an oxidative additive step, addition step, where H and H would be occurring at the trans fashion. So here, if you are having a phosphine group, another phosphine group, and Cl group, this H would come at the cis position. Now, the second step that we are introducing here. So here we are introducing our alkene, which is the substrate, CH2. This is the second step. So firstly, the alkene is going to have a coordination with the metal center, the pi electron interaction, CH2, and your one H, and it's still in cis mode, and other things are intact as it is. Now, when you have this way, your alkene is going to coordinate, insert in your rhodium metal bond, and therefore one hydride is going to be transferred into one position at this position. So ultimately, it would form like it would be forming RCH2, CH2. Now, earlier it was a pi bond, now it's a sigma bond with rhodium. Phosphorus is there, phosphine is there. One H is left, another H is here. The other H is already been transferred here. And then if this goes here, this will be transferring here. This would be having a minus charge, which will coordinate with your rhodium. Now, ultimately, your this moiety and your hydride, they have to be in cis position. Right now, they are in trans position. So R, CH2, CH2, RH. Here there is one P, another P, and one H in here. Now, when they are in cis position, they can release the product as RCH2CH3, which is your product, and gives back your catalyst, because ultimately it would only left with phosphine, and Cl. So sorry for the clumsiness over here, but there is not much space over here. So ultimately, we got an alkene as our product, and we regenerated the catalyst back to its form. So this has been given by Halpern in 1976. Let's look out the steps that we have talked about here. So what are the steps that we have seen? Steps in hydrogenation of alkene using CpH3 rhodium chloride, which is nothing but your Wilkinson catalyst. So the first step is step number one. Step number one is your oxidative addition of dihydrogen. Dihydrogen. You can see here, this is your first step where the dihydrogen is going to get added onto your rhodium catalyst, making it from +1 state to the +3 state, and then regaining the same oxidation state after reductive elimination. So the step two that we have is it's your coordination of your alkene, the substrate. Coordination of alkene. That's also we have seen that this is your substrate and this is going to coordinate as a pi interaction. Third step followed by this one was the alkene insertion. And this is your rate determining step. It's a very, very slow step. That's why we can determine the rate over here. The step 4, as in when alkene has been inserted, there would be a trans and cis isomerization where the hydride and the other part of the alkene group has to be in a trans form. Like this, right now, this and this one is in trans, and here it becomes in cis position. So this step is very, very important. This is your fourth step. And ultimately, the fifth step is your reductive elimination, which is this one. So step number six, five is a reductive elimination. Reductive elimination, it's the complementary of your oxidative addition. So here what really happens, as we mentioned, that M in N plus oxidation state, it goes from Mn to Mn plus 2 if hydride is going to get added. And this is called oxidative addition. And the same process when you have this is in cis form, and when it releases the hydrogen back, it would regain Mn plus to say Mn plus. So this is your reductive elimination, and for that step to happen, you need to have your both moieties which are going to go out, they should be in your cis position. I hope this is clear. If there is any doubt regarding the mechanism, please let me know. Otherwise, we can move ahead with another example of catalyst. Okay. So now we can move with another catalyst can be used for the terminal alkenes. So topic would be hydrogenation of terminal alkenes using PPH3 thrice sodium HCO. So this is the catalyst now. Again, it's in plus one oxidation state because of the one hydride. So here, what would happen? So here it is happening when you're not, the H2 is not the first step which is going to happen. So let's look into the mechanism. I'll show it in the next slide. So firstly, we are taking up the catalyst where it is in PPP chemistry. And here again, P is your PPH3. Firstly, we will be having a loss of one PPH3 moiety, making it as rhodium, CO, phosphine, and phosphine group. The first step here, it would be having a alkene coordination, as we already have a hydride connected to the metal center. So what will happen? Rhodium, then we have phosphine here, H here, CO, and it is coordinating with CH2 and CHR and CH2. Now we know that once the coordination will happen, it is going to have a insertion where metal hydride bond, it would get inserted into the metal hydride bond. So the hydride is going to transfer onto one side, which is your this side, and therefore it is going to connect here. The CO, sodium, phosphine, phosphine, another group is CH2, CH. So always the hydride is going to transfer where you are having a less number of hydride already present. Now after this, you are introducing now hydrogen. Now at this step, the oxidative addition will happen. So it will happen at a cis fashion, phosphorus, phosphine, CO, CH2, CH2, and R. Now ultimately, since these two things are in cis to each other, it would release the product as CH3, CH2R, and again giving back your catalyst, which is your fourth step. So this is a different mechanism if you are starting with a metal hydride catalyst itself. So here, what would be your steps? Your step number one was the coordination of the alkene. In case of the metal hydride catalyst itself, this is the first step. The second step is the insertion of your step number two is the insertion of your alkene into the metal hydride bond, then oxidative addition of dihydrogen H2, and step number four was to have a reductive elimination. So when there was no hydride into your catalyst, you started with a process called oxidative addition. Then you had coordination of alkene, then insertion, and then followed by reductive elimination. But here, since you already have a metal hydride bond in your system, that is easy for the system to take up and coordinate with the alkene without having additional hydrogen over there, and then following the path and going from insertion to metal hydride and then from an oxidation. So I hope this one is also clear. Then we can move ahead with our asymmetric hydrogenation of alkenes. If there is any question regarding the two different methods, methods is actually the similar, mechanism is similar. The only thing is based on the catalyst what you have chosen, which step is going to be happening at the first stage, like whether it is going to be the oxidative addition or it is going to be the coordination of alkene, whatever be the step that you have to analyze regarding the catalyst that you are taking into consideration. Now we can move ahead for the asymmetric hydrogenation of alkenes. So this we have already discussed earlier. Last time we talked about the asymmetric oxidation. Whenever there is a chirality induced, be it coming from your catalyst or your ligand, it would end up having the asymmetric oxidation addition. So here we are saying that we are already having a, we can say that the catalyst that we are choosing here is a chiral catalyst. So, and that I'll define by star. Let's see the example. So we are taking a rhodium based catalyst, which is a chiral catalyst. And here it is coordinating with a quad system. Which way you are asking, like PPHCr, HCO, Cl? The previous reaction you are asking here, right? So here the catalyst is your HCO and three phosphine groups are there with an oxidation state of rhodium as +1. Where already the metal is having the hydride over. Because presence of hydride only, it is involving the alkene to coordinate it with first. If there is no hydride over there, and if you are using a PPHD2 RHCOCl, firstly you have to have a hydrogen to get activated, and then only there would be a metal hydride bond. Say for example, the earlier case we were having the PPHD RHCl. That was your first, and there was no hydride, right? And in that case, we introduce the hydrogen and oxidative addition happened. This is a different kind of catalyst where we have a three phosphines and it is a TBB geometry. The earlier one was having a distorted tetrahydrogeometry. This is having a 5 coordination number where three phosphines, one metal hydride, and one carbonyl group is there. And only what we are leaving over here a phosphine group because the carbonyl group will be strongly bound with your system. And then you are introducing an alkene which is coordinating with your metal center. Is that clear? If you still have any doubt, please let me know. These are two different systems. Firstly, that what we use that was a Wilkinson system having only the phosphine and one chromium group, and the charge was coming from a chloride. Here, the rhodium is in it's in five coordination number. It is having five moieties around it, which is because of the metal hydride bond, it is allowing the alkene to coordinate first rather than having an oxidative addition step there. Earlier case when they where it is having a space also when four coordination is possible and one when we have left one phosphine, again the two moieties can come over there. Here it is already having a four coordination around it, so it is firstly involving the alkene to coordinate and participate. Is that clear now? So yeah, there we go. So this is another type of catalyst. Now this is different type of sodium catalyst with a four coordination number. And here we are taking a cord, which is a cyclooctadiene system. So the cord would be there where only the two moieties, this is participating here. So it is basically a cord system. This is a cyclooctadiene system. Now the star is saying that it's a chiral in nature. So at firstly, it would take, now in this system, firstly, it is taking a two dihydrogen molecule to release this cord molecule and it would release it as an H8C8H16. And if you are doing it in a solvent, obviously it is a homogeneous medium. So these particular systems, when it is getting hydrogenated, it is going out. So the left out coordination number would be filled by your solvent molecule, which are just coordinating with your system, right? And could be having an overall charge of plus outside to have to give a moiety a sign. Because phosphine is also going to bind to a lone pair and solvents also does not carry any charge. So this kind of system when we are taking and when it is participating in the reaction, it is also again going to go through the same process. So now we are starting with our active system, which is rhodium, solvent, and solvent. Now the first step would be, now here also since we have already used the hydrogen molecule and the four coordination is completed. So this particular catalyst also follows a coordination at a faster rate compared to the oxidative addition because that hydrogen has first been used for removing your cord over there, the ligand. Now it would first form this RH and having a coordination, the one solvent molecule, the coordination with CH2 and CH2. Now followed by at this step, different catalysts are going to follow the different path depending upon what step is the fastest in their case. Now at this step, since the coordination has happened, but it does not have a metal hydride to have an insertion to happen. So the next step would be your insertion, where firstly the oxidative addition would happen and it would remain as a coordination system. Now the insertion would happen, this hydride is going to bind with your system here and it would end up making HCH2, CH3. Since the coordination number would be free, so it would be having again back the solvent because it would be there in the system. And ultimately, since these two are in cis position, again it would release your product as CH3, CH3, and you will left out with your active catalyst, which is this. So the different systems, as we saw, three different catalysts based on the rhodium. First is Wilkinson catalyst. The second one was having an hydride already. The third one is having a ligand which can be hydrogenated first and then it can leave out. So all the systems, they are following the same mechanistic route that coordination would happen, insertion would happen, oxidative addition, and the reductive elimination. But the step number one, step number two, they would be different from the previous one. They won't be same for all the systems based on how the catalyst has been designed and what is the fastest step, what is the slowest step. Based on that only, there will be competition whether oxidative reduction is going to happen first, or it is going to coordinate with the alkene first. So is that fine? Is that clear? Okay. Now, some more specific example of the asymmetric synthesis that we can see. So we have now, as I mentioned, that the catalyst with the formula LRH solvent twice and one positive charge outside because your ligand is neutral as well as your solvent. So the positive charge is coming at the coordination sphere because of some anionic path, counter anionic path, which is outside that we don't need to worry about. So here, uh, this is this catalyst along with the chiral diphosphine ligands, which we were mentioning as P, they hydrogenate the prochiral, which means the alkenes which are not chiral, but they have a tendency to get chiral, give the chiral alkenes or products in high energy selectivity. What it is trying to say, like so here we we saw in earlier case we had this diphosphane system where rhodium was there and we had the solvent molecule and we said that this is a chiral system. The chirality was coming from this chiral diphosphane. So this molecule was chiral in nature. How we have certain certain structures where CH2, PPH2, CH2, PPH2, where the phosphorus is going to coordinate with the metal center, and then it is coordinated with oxygen. Here it is coordinated with oxygen. This is CH3, and this is CH3. So this particular center, if you see, it would be having one hydrogen, one CH2, one oxygen, another bond with carbon, another different carbon. So these centers are your chiral centers. These two are your chiral centers because all their bonding are different, making this diphosphane as a chiral diphosphane. So this is one type of ligand which is called as the IOP, and this can be used in place of this PP, which would use the chirality in your system. The another example that we have is, okay, this meeting is going to end in 1 minute. So I would request you to rejoin the link and just end it here.